A new paper for training reasoning models. Usually the problem is reinforcement learning reasoning models, they just check the final step. And so even if there are incorrect reasoning steps that lead to correct final step, they reward that whole reasoning process if the final step is correct. I mean the final answer to the question. If it's correct, all of the steps, even if they are incorrect, are rewarded. This method comes up with a new way to check each reasoning steps, not just the final answer. So we teach the LLM to have correct reasoning steps and not just randomly luckily get to correct answer with wrong reasoning steps. First, we will train the LLM or tell the LLM to generate its reasoning steps in these chunk tags, because otherwise it's difficult to know what exactly are reasoning steps. So LLM will generate reasoning steps in these chunk tags, and then each chunk tag we will check separately, evaluate separately as a reasoning step. So for each of the chunk tags, we check, we generate the complete completion 16 times, for example. And then how many of those 16 completions, starting from the current chunk, lead to correct answer? The more of them lead to correct answer, the better this chunk is. But generating 16 completions for every single chunk in every single response is expensive. So we will actually train another judge model, and we will train it to judge the chunks without the completions. So we will train the judge model by just giving it the chunk and the score for that chunk. And the score for that chunk is calculated based on how many completions of the 16 are correct. But the judge model will now learn to evaluate a chunk with a score without needing to generate 16 completions. We just generated the training data to train the judge. So now judge will be just able to look at the chunk and assign a score if it's good or bad. And by the way, so we will not assign like score from 1 to 16 or something. We will just have good or bad, and it will be, for example, based if more than 10 are good, like 10 answers are correct, 6 are incorrect, then that's a good chunk. Another method would be if more answers are correct than with the previous chunk. So remember, LLM is trying to reason using these chunks. And if it generates the next chunk, and now all of a sudden more of the 16 answers are correct, this means the chunk provide improvement compared to the previous chunk. So it figured something out new. So now the judge will learn to evaluate this chunk as good because it provides improvement. Now more answers are correct. For example, more of these 16 answers are now correct, so this is an improvement. So now let's explain this paper step by step, and I'm going to explain this all over again, but step by step. The big picture, the problem, and the solution. The problem: LLMs are now solving complex math and logic problems by generating a chain of thought, a series of intermediate reasoning steps. The challenge is ensuring these intermediate steps are logically correct. The traditional method of only checking the final answer, called outcome reward modeling, is inefficient. A single mistake early on can ruin the whole situation, but you only find out at the end. A better approach is process reward modeling, which evaluates each step of the reasoning. However, the paper points out two major flaws with existing PRMs. They are black box classifiers. They simply output a score or label correct, incorrect for a step without explaining why. They don't generalize well. They are typically trained with supervised fine-tuning on static, pre-labeled dataset, which limits their ability to adapt to new reasoning patterns. Also, the problem is that LLM is gonna start reward hacking, and it's not gonna solve the task, but create some hacks or avoid what we intended it to do, but just to get more reward. The StepwiseR solution. The authors propose a radical shift. Instead of treating the evaluation of a reasoning step as a simple classification task, they reframe it as a reasoning task itself. I really like this. Their model, StepwiseR, is a generative judge. When asked to evaluate a reasoning step, it first generates its own chain of thought explaining its analysis. This is called meta-reasoning, reasoning about reasoning. Only after this analysis does it deliver a final verdict. Crucially, this judge is trained using reinforcement learning, allowing it to learn and improve in a more dynamic online fashion. There are three steps in StepwiseR method. Chain of thought generation with self-segmentation, chunks of thought. The problem: what defines a step? Simply splitting the chain of thought at every double new line is a poor heuristic, so this is new paragraph. It often breaks up a single logical thought into multiple incomplete fragments. So when you want to reward or analyze a step of the LLM, what is a step? So how do you separate a single step? How do you see what a single step is? You cannot just do like a double new line because there could be an equation that's correlated to the sentence above, so that's still a single step. This makes it difficult for a judge to evaluate any single fragment in isolation, any single part of the LLM output. The solution: teach a policy model to segment its own reasoning into logically coherent units, which the paper calls chunks of thought. How it's done? They generate a set of correct chain of thought solutions from a base LLM. They use a more powerful LLM Llama 3.170b with a specific set of rules, see table 1, to segment these solutions by inserting chunk tags. The rules ensure each chunk has a unified purpose and represents a complete logical leap. They then fine-tune the original base model on this newly segmented data. Result: the policy model, which is the LLM that generates text, learns to automatically generate its reasoning in these well-defined, self-contained chunks. This provides a much better unit of analysis for the judge and replaces the total number of steps that need to be evaluated, saving computational cost. Stepwise data annotation, labeling the chunks. The goal: now that we have reasoning trajectories broken into meaningful chunks, we need to create training data for our judge. This means assigning a good or bad label to each chunk. The method: they use Monte Carlo rollouts to estimate the Q value, success probability before and after each chunk. So let's see, Monte Carlo rollouts, a simulation technique. To evaluate a step, you let the model generate many possible future paths, rollouts, from that point onwards. The quality of the step is then estimated by the average success rate of these rollouts. Average success rate of the rollouts estimates the quality of the current step that generated all of those rollouts. Q value: in this context, the Q value of reasoning step is the estimated probability of reaching correct final answer, starting from that step. It's calculated using Monte Carlo rollouts. So Q value is assigned to a step and it's calculated by checking using Monte Carlo rollouts and seeing how good rollouts, how good future steps this step leads, and the probability of success of all of those future steps. For each chunk, they estimate the Q value before the chunk was created and with that chunk created, to see if that chunk is gonna increase the probability of correct answer in the end. Each Q value is estimated by generating M, for example, 16 full completions from that point and calculating the fraction that led to a correct final answer. The more led to a good final answer, correct final answer, the higher the Q value is. Based on these Q values, they assign a binary label, plus for good, minus for bad, using one of the three strategies. Absolute Q value, the simplest method. If the Q value after the chunk is greater than 0, the chunk is labeled good. If it's 0, it's bad. Relative effective reward, rel effective. This strategy rewards progress. It considers not just the final Q value, but also the increase in the Q value from before to after the chunk. So how much did it increase the Q value? A step that raises the success chance from 10 to 50% is rewarded. A relative ratio, rel ratio, a simpler relative method. A chunk is good if the ratio of the Q value after to the Q value before is above a certain threshold. For example, 0.8. The paper finds that relative signals, rel effective and rel ratio, produce better judges because they incentivize forward progress rather than just avoiding terminal failure. Step 3. Training the judge via reinforcement learning. The goal: train the stepwiser judge using the label data from step 2. The method: instead of simple supervised fine-tuning, they use online reinforcement learning. task formulation. The judge is given the problem, the reasoning, history, and the current chunk to evaluate. It is prompted to first generate an analysis, its own chain of thought about the chunk, and then a final judgment, boxed positive or boxed negative. Reinforcement learning reward. The training signal is simple. The judge gets a reward of +1 if the final judgment matches the label derived from the Monte Carlo rollouts in step 2 and 0 otherwise. So they use Monte Carlo as the real judgment, and then they are training a judge to just reason about if this step is correct. And judge needs to learn how Monte Carlo would evaluate it. Optimization algorithm. They use GRPO, and a reinforcement learning algorithm designed for training generative models. The judge generates multiple judgments, receives rewards, and updates its internal parameters to produce better analysis and more accurate judgment in the future. Prompt dataset balancing. They observe that good chunks are far more common than bad ones. To prevent the judge from simply leveraging to always predict positive, they balance the training data by downsampling the majority class. This was found to be critical for stable training and good performance. Okay, so most of the chunks are positive, are good. So I guess they want to actually make more bad chunks in the training dataset, so the judge doesn't always just say positive, good, this chunk is good. So they evaluate StepwiseR on these benchmarks, and it performs well. They also use the judge to curate better fine-tuning data. How it works: generate multiple solutions for each problem. Instead of picking the one with the correct final answer, use StepwiseR to score every chunk in every solution. The solution with the highest average chunk score is selected. Result: fine-tuning a model on this high-quality judge-selected data produces a stronger final model compared to other selection methods. That's it for this video. Check out other videos on my channel and join my Discord where we do AI research.